Hello everyone. What we're going to be doing today is we're going to be looking at section 2.4, distribution shapes. And you wondered last section probably, why do we have to do a histogram? Why do we have to do a dot plot? Why do we have to do a stem and leaf? Well, these histograms, pie charts, bar charts, whatever, tell us the distribution of the data. And these distributions have certain shapes that can tell us a lot about the data and help us do a lot of statistical analysis on it. So, for instance, if we look at this one, notice that the overall shape of the distribution is a smooth curve. Now, it's not perfect. Notice not even the bars are symmetrical or anything like that, but they're close. As a matter of fact, this is jumping a little ahead, but notice here, this isn't symmetrical. Look how these are off centered here. Some of them are, some of them are, but it's close to being symmetrical. In real life practical applications of distributions, very rarely will you have something that is perfectly symmetrical. So as long as it's close to being symmetrical, we would say that this is a symmetrical graph or distribution, excuse me. So this helps us determine the shape and what the data is doing here, what the data is doing, whether it's clustered, spread out, and so on. So we have some common distribution shapes. Bell-shaped, you've heard of that because you may have been graded by a teacher that used a bell-shaped curve to curve your grades. Um, Triangular, uniform, reverse J, J-shaped, right skewed and left skewed are very common. Bimodal and multimodal. Okay, these are the different distributions. Now, our last picture that I showed, this one right here, this is not a This does not form a perfect bell curve. It's not perfect, but it is a bell curve nonetheless. Um, like I said, in practical life, perfection is not achievable. Okay, now there are instances where we can have it in data collecting, but more times than not, it's not. So you have to be general about how you're describing these shapes. So, and as I said, a distribution only needs to approximate it, okay, to get a name. It doesn't have to be exact. So notice, this is uh, this is what we would call a right skewed graph, okay? Notice this matches our right skewed distribution, but notice how our data is not necessarily filling in our graph, so to speak. It's not necessarily perfectly right skewed, okay? But it's generally right skewed. And so it only has to approximate the shape. So please keep that in mind, especially as you're going into MyLabs Plus or on exams and things like that. Don't try to overthink this. A lot of times students will overthink the shapes. Approximately, okay? Approximately is the key word. All right, so modality. When you look at the shape of distribution, you're going to notice whether or not it has peaks. A unimodal graph has one peak, obviously. Bimodal has two. Multimodal has three or four. Now, technically speaking, if we get into the technicalities of math, a distribution is only bimodal or multimodal if the peaks are the same height. Now, as I've said, in practice, rarely are do things come out to be perfect. When you're data collecting, there rarely in a real world situation, rarely do you have perfect definition bimodal or multimodal graphs. So in practice in a real world situation, we would probably declare something as bimodal or multimodal even if the peaks are not the same height. Okay, even if they're not. So here's some modality. Notice that bell shape, triangular shape, uniform, reverse J, J, right skewed, and left skewed. These are all unimodal graphs. One peak. Unimodal graphs. Um, Now, there can be an argument, and I'll tell you about the uniform graph here in a minute. But then we have bimodal and multimodal. That's what I mean when I say a bimodal graph having 2 peaks, multimodal having 3 or more. Okay. Now, the uniform graph is under a bit of controversy. A uniform distribution has either no peaks or infinitely many peaks. It depends on how you look at it. In any case, we want to leave uniform out of the modality classification. Just don't classify uniform, because it's either going to be one or the. It just depends on how you're looking at it. When something is a opinion, when it cannot be statistically backed up, then it's our interpretation, and with human interpretation comes human error. So we just want to leave letter C out right there. Okay. Hopefully that's understandable. All right. So symmetry. Now I know you remember things being symmetric in geometry probably, and obviously symmetry is the same thing here. If it can be divided into 2 mirror images, then we say it's symmetric. If you can draw the graph in the middle of a sheet of paper, fold it in half, and get 2 identical images, symmetric. Bell-shaped, triangular, and uniform are usually symmetric. Bimodal and multimodal can be symmetric, but they're not always symmetric, obviously, because you can have more peaks at one end than you have at the other end, and things like that. But you can have the same number of peaks on both sides. So exact symmetry, as I said earlier when we looked at that first graph, exact symmetry is not required to be symmetric. It just needs to be pretty close, because remember, we're talking about real world situations here. Okay. Skewness. A unimodal distribution that is not symmetric is either right skewed or left skewed. Let me say that again. A unimodal distribution that is not symmetric is either right skewed or left skewed. Now, right skewed is where we rise to a peak rapidly and then come back to horizontal slowly. So rise to a peak rapidly, come back to horizontal slowly. Okay, that would be right skewed. Left skewed rises to a peak slowly and comes back to horizontal rapidly. Okay, right skewed versus left skewed. All right, so there's better pictures than I can draw freehanded on your distribution shapes on page 72 in your book. Those distribution shapes are on page 72 in your book. So make sure you memorize those shapes. Reverse J shape and J shape are special types of right and left skewed. And if you look at it, you can see what I mean. A reverse J is very similar to right skewed. Reverse J looks something like this. A J shape looks something like this. So these are just different special types of these distributions. Okay, special types. All right, so if you have any questions, this is a short section. I know you love that. So if you have any questions, please ask. I hope you do well on your homework.